And so the way that we can categorize how extreme a bias is, we don't just want to look at the bias, the size of the bias in absolute terms, because we lose sight of how big is the quantity that we're approximating. So when we are approximating, for example, a ratio of two things, we wouldn't expect, first of all, that ratio can't be negative, and that ratio sort of has a ceiling on how big it could be. Whereas when we're estimating the bias of a variable which has really big values, then getting a big bias might not be such a big thing. So these are relative um, calculations. So we'd want to think about how big is the bias relative to how large the quantities are that we're estimating. So that's why we look at a ratio to give us, relatively speaking, how big is the bias compared to the variability in our sampling. So on the bottom of this, we have our bootstrap standard error. And so that's measuring kind of the variability due to sampling. And on top, we have our bias. So what we'd like to know is relative to how much variability we have in the sampling, how large is this bias? And so as a rule of thumb, if that ratio exceeds plus or minus 0.02, then we say that that bias, that's what we would consider a large bias. So this is just kind of an informal rule of thumb. And at that point, you just need to acknowledge that you might have, this bias might have a substantial effect on the accuracy of your estimate. So let's take a look at an example and maybe see why we might want to compare ratios instead of just thinking about the bias in absolute terms. So here are two examples that we've looked at so far, amongst many others. And so one of them is this Verizon example, and the other was we looked at a sample of data of groundwater samples taken in Bangladesh, and we calculated what the mean arsenic level was in the groundwater in Bangladesh. At least we used a bootstrap distribution to come up with a confidence interval estimate for the mean amount of arsenic in the groundwater in Bangladesh. So on top, we would calculate the bias. And so since we don't know what mu is, for the arsenic example, we would estimate the bias with the bootstrap distribution. And so what we found was the original sample had a mean of 125.320. So that's like our theta hat. And the center of our bootstrap distribution was 125.229. So taking that difference, we see that there is some negative bias here. So there is some bias because we're not getting 0. And then we would divide by the bootstrap standard error, which in that example, I got to be 17.9. But one thing that you want to keep in mind is even if you run the same R code as I am, you're going to get slightly different values because you might be generating different bootstrap samples than I did in mine. So there's some randomness involved here. And calculating this ratio gives us minus 0.005. So relatively speaking, that's small bias. And if we were to compare that to the Verizon example where we found that the amount of bias, or at least the estimate for the bias, was 0.03. So that was the difference between the bootstrap, the center of the bootstrap distribution and the ratio of the means that we got in our original sample. And the standard error is approximately that I got for my bootstrap distribution on the previous slide was 0.133. And so if we take a look at that ratio, that comes out to 0.226. And so relatively speaking, that's a pretty big bias. So in absolute terms, the actual bias, the numerators are pretty close to each other, but relatively speaking, we have much more variability in the sampling in the arsenic example. So having this small bias is really not that big of a deal whereas with the Verizon example, we did not have a lot of variability in our bootstrapping because we're dealing with pretty small numbers to begin with. So this bias of 0.03 is actually quite big. And so our confidence interval that we constructed a couple of slides ago, there's going to be some effect of that tail that we saw on the right on our confidence interval estimate.